a little bit about Chris. Chris is a registered professional engineer in BC with over 20 years experience in water and wastewater treatment. He graduated from the University of Plymouth in England with a degree in civil engineering. He's worked for both private and public sector organizations in Europe and Canada, and is currently responsible for municipal business development in Western Canada. So with my pleasure to introduce you to Chris.
Great, thank you, Jim, and thank you everybody for choosing to listen in on this presentation. So 2 things you should know about grit removal. There's probably more than 2 things you should know about grit removal, but hopefully there's even more than 2 things in this presentation that I'm about to give that'll be of interest. But clearly it's all about grit removal. So what is in the presentation? Firstly, I'm going to talk a little bit about the big picture, the context. What is grit? Why should you remove it? Then something quite specific around grit measurements. Then into the technologies. How do you remove grit? And a little bit about a technology that we've recently introduced onto the market. If you wanted to ask questions as we go along, probably chat's the easiest way to do that. And certainly if it's sort of, as part of what we're talking about at that point, then we can answer the questions right away. Also, I'll try and leave a bit of time at the end of the presentation, so for questions at the end also. Okay, oh, sorry, wrong way. Okay, so what is grit and why should you remove it? So starting with the why remove it, this is probably not going to be a surprise to people who operate wastewater plants. Grit settles, it's dense, so it's going to settle out, and it's typically inert as well. That means it can accumulate in basins, things like bioreactors, digesters. It just fills up space. Those sort of processes are designed based on retention time. They need a volume to do their job. So if some of that volume is occupied by grit, then the performance is going to decrease. You've got less volume to do the job. And that can affect the process performance as well as the efficiency, things like mixing or aeration, for example. Grit is also typically abrasive. Hard, inert material causes wear on things. So you're going to see premature failures, increased replacement frequencies, things failing in the middle of the night, don't they always? So those are really the reasons why you want to be thinking about removing grit. I think it's safe to say that for most mechanical plants, probably just about all mechanical plants, grit removal is a useful thing. Even on lagoon systems, grit removal isn't a bad idea because it just fills up your lagoon with inert material if you don't remove it. So it's a pretty common thing on most wastewater plants these days. Okay, so what is grit? This is where it starts to get a bit more interesting. It's not so simple. We used to consider grit or characterize grit, design our systems around grit, thinking it was sand. So you can see here, this is the old definition. Spherical, clean, silica sand, 2.65 specific gravity, nice and dense. So that was how we used to design things like aerated grit channels, for example. But we still found grit accumulating downstream in our wastewater plants. So that characterization was a start, but it maybe wasn't quite as complete, as nuanced as it needed to be. What we now realize is that grit is not all nice clean sand, it's all sorts of material. And you can see the photograph on the right of the screen here. That's a grit bin, so that's what you remove in a grit removal system at a wastewater plant. And you can see it's not all sand, it's all sorts of different things. Eggshells, for example, most people would probably consider eggshells grit. It's inert, it's fairly dense. Coffee ground, maybe not, probably not, but who knows? It could occupy volume, I guess. So it's a gray area. It's all sorts of different things. This leads on to something, maybe the first thing that you might not know, maybe you already do, but something that a lot of folks I speak with are not so familiar with. And that is that grit, when it comes into a wastewater plant, is rarely clean. It's wastewater, right? It's got stuff stuck to it, organics. Think of your eggshell again with some bacon fat. Not an unusual scenario. So if that piece of eggshell or whatever other piece of grit has got something stuck to it, like fat or organics, it's not going to behave like a nice dense particle anymore because it's stuck to something lighter. So that affects its density, and that affects how it behaves, how it settles, most importantly, and how easy it is to remove, therefore. So that's one of the reasons you need to be thinking about organics when you're thinking about grit removal. Those two things kind of go hand in hand. Grit removal really, an important aspect of grit removal is separating organics from grit. And the sort of other aspect of that is partly to do with the removal, the settleability, but it's also because you want organics in the wastewater plant. That's what it's there for, right? To remove organics. You don't want organics in your grit bin, where they're going to stink, where maybe the landfill's not so happy about receiving that stuff. Some people even reuse grit for things like road base, for example. So you certainly don't want dirty, organic, stinky grit if you're going to do something like that with it. So when we look at grit, the sort of nature of grit, the characterization of grit, what's likely to come into your wastewater plants, it does vary. You can see that on the graphic here. So there are design guidelines available. What is typical grit in a given area in North America? You can see this is pretty broad brush though. So it does vary between locations, between different geological sort of formations, for example. But maybe the most useful is to start looking at it at a more specific level, your specific plant, your collection system. There you do see a lot of differences between collection systems. Good example of that would be combined sewers versus separated sewers. So if you've got a combined sewer, it's designed to receive surface drainage. You're likely to have more grit than you would if you had a separated sewer, a sanitary sewer. So that's certainly, you do get significant variations between systems. You also even get differences over time. So if you've got a lot of construction going on in your, the area of your collection system, people digging up roads or whatever, that can also cause more grit. So it does vary quite a lot. That's the point. And that leads into the grit measurement. So why would you want to even think about measuring grit? There's really two reasons why you might do that. One is to get a sense of what's coming into your plant, a characterization study. How much grit do you have? What sort of grit do you have? Is a lot of it really fine? If you've got a lot of really fine grit, that might push you towards doing a different type of grit removal system versus if you just had sort of larger grit. So a characterization study is one reason for measuring grit. The other reason, and probably this is the more common reason, is to measure removal performance. So for example, you've done an upgrade, you've put in a new grit removal process at your plant. Does it meet guarantee? How well is it working? Does it do what the manufacturer said it would? So validating performance, that's probably the most common reason why people would do a grit measurement study. Okay, so if you're going to measure grit, how do you do that? This is where it starts to get really interesting. It's not so simple. That's maybe the takeaway from this slide. There's quite a lot to it. So firstly, you need to get a representative sample. When you look at the computational fluid dynamics graphic on the top right of the screen there, you can see that the velocity, that's showing velocity around a grit chamber. You can see that the velocity, especially in the outlet, that's the bigger channel, the lower channel there, a lot of difference in velocity across that channel. So if you were to sample from just one location, you might not get a representative sample. You might have too much grit or not enough grit, depending on where you were in the channel. So getting a good representative sample means having extraction points, taking your sample from multiple points within the channel in terms of depth and width as well. So how you would do that is you would have a bunch of sample tubes mounted on some kind of frame typically that you could lower down into the channel. And then those tubes connected to pumps. You can see that on the middle photograph there. Peristaltic pumps is quite common for that. Drawing the sample from multiple locations in the channel, width and depth. And if you're measuring the performance of a grit removal system, you would do that on the influent channel and on the effluent channel, and you would run that all at the same time, so you know exactly what's been removed by the grit removal system. Bottom line is, with that sample, you need to get a sense of the particle size distribution. So how much grit have you got of this particle size range, and then so on and so forth. And you do that by sieving. You can see on the bottom left there the sieves. So it's like a geological sort of sieving thing. You have a stack of sieves, graduated sieves with different mesh sizes. So sieving is how you work out the different particle sizes. And you need to weigh it to know how much you've got, the mass of each of those particle sizes. So that's what you're aiming for, is sieving for particle size and weighing to know mass. But before you can go there, or maybe as part of that, you probably need to do something to your sample. And this is, as I say, where it gets really interesting. So maybe just to go back to, you've got your sample, you've been pumping those pumps, you're filling up those cone bottom tanks. You do that for a good few hours, 6-8 hours is fairly typical. Collecting the grit, you overflow the water, you're trying to build up enough grit in the bottom of that cone bottom tank so that you can do some analysis on it. So you need to run for that sort of a period of time to get enough grit to do a decent analysis. So after you've filled up that tank, or you've got enough grit in the bottom of the tank, drain off the water, get the grit sample out, and then what do you do with it? You can do what's called wet sieving, where you put that raw sample on the top of that graduated stack of sieves and then wash it gently through. So that passes the sample through those various sieves, stopping each of those particle sizes as it goes on those graduated sieves. So that's called wet sieving. You could dry the sample and then put it on the sieves and kind of shake it through, and that's called dry sieving. You can even burn the sample to work out how much organics you had, so weigh it before and then burn it and then weigh it after, and that will tell you how much organics you had in the sample. So those are some of the things you can do. Something else you can do as part of that wet sieving analysis is you've got now your wet sample which is stopped on each of those sieves. So you can empty out a sieve and put it in a settling cone. The settling cone measures settling rates, an Imhoff cone measures settling rates. So you see how long it took for the sample to settle out at the bottom of the cone. That tells you a settling rate. And then what you do with that is you equate that settling time to what it would be if it was clean sand. And that gives you what's called a sand equivalent size. So it's a bit like going back to that earlier slide about what is grit, the whole sort of silica sand characterization of grit. We know what sand is, we know how sand behaves. So if it settles at, let's say, I don't know, it takes 5 minutes to settle, then we know exactly how big the grains of sand would have to be to take 5 minutes to settle in that Imhoff cone. It is a benchmark, it is a known standard. So that's why you do this, to equate your raw sample of grit, which is all sorts of different things, with organics still on them at this point, because it's a raw, wet, sieved sample. You haven't dried it or burnt it. And we equate that back to sand. So that's called sand equivalent size. And this is another thing that I often speak with folks about, and they're a bit surprised about maybe, is that there's actually no agreed standard test method. There's no one single way of doing this that's written in the textbooks or whatever that everybody does. There is no single agreed upon standard test method. Now that sometimes surprises folks. Well, that isn't good, right? Surely there should be. It's not so easy, and there's folks been working on this for a while. Broadly speaking, you could say there's some top-down activities, initiatives being taken to tighten this situation up, and there's some bottom-up kind of things happening in the industry as well. So from the top down, a good example of that would be the Water Environment Federation, WEF. They have a task force that's been formed a good few years ago now, working on this. They recently published this document that you see on the right there, the guidelines for grit sampling and characterization. And that's helped a lot. That's moved things on. In those guidelines, they don't have a single test method, but they do have a number of recommended test methods. So it's kind of narrowing things down, good ways of doing this. There's also, on the bottom-up side, there's a kind of industry consensus forming, you could say, where folks like consulting engineers are defining, if they're going out for a project, they would put a specification in the request for proposals, and that specification might have a grit testing method as part of it. Do it like this. We're buying a new grit removal system. This project involves a new grit removal system. It needs to meet this performance, and it needs to meet that performance based on this method. So that's also happening in the industry as a sort of bottom-up. Manufacturers have also been part of that. Folks like us who build these systems, provide this technology, also coming together on a way of doing it. In broad terms, how Veolia would recommend that test method is done, our testing standard, and the basis on which our performance statements are now made, is a combination of both the wet sieving with the sand equivalent size analysis and the dry sieving. So it's, you could say, the best of both worlds. It kind of looks at it from different angles and comes at a common number, combines all of that into an average, and that's what we would base our performance statement on. And there's others in the industry doing it that way as well. Okay, so that was sort of the big picture stuff. Maybe now getting into some of the technologies. How do you remove grit? So firstly, maybe where do you remove grit is a good place to start. In your headworks, in your pre-treatment system. If you're doing screening, and you probably are, then for a mechanical plant for sure, then you would put it downstream of your screen. Some people do 2 stages of screening, coarse screening followed by fine screening. With a grit removal system, you could put that in the middle. You could put it after the coarse screen. It would certainly be good to put it downstream of your first screen. And if you only have 1 stage of screening, then yeah, you put it after the screen. Some things to be thinking about when you think about what system would work for you. So what removal performance are you looking for? Are you trying to protect a really sensitive process, maybe something like a membrane bioreactor, for example, where you really don't want a lot of grit on your membranes? Grit is abrasive and membranes are sensitive to abrasion, so that might be a reason to go with a really high performance grit removal system. Or is it a lagoon and, you know, enough is enough kind of a thing? Whatever you can get out would be great, but it doesn't have to be the best possible performance. So that might be something to think about. You know, how big is your plant? Maybe factors in that as well. How much space have you got? And then O&M complexity, operations and maintenance complexity. To be fair, grit removal systems aren't particularly complicated. Even the more advanced ones, the more higher performance ones, they're still pretty simple. And I'm going to be talking a bit about what is involved in operating and maintaining these things a little bit later in the slides. So, but that might be something to have in mind. I think it's safe to say that if you've got a mechanical wastewater plant, then the amount of operation and maintenance benefit by putting in grit removal it far outweighs the amount of O&M that it's going to take to run that grit removal system. So if you don't have a grit removal system, you're going to have grit throughout everything in your plant. All of your systems, your mechanical equipment are going to then suffer from that grit. So it's going to make much more O&M sense to have a one little bit of O&M in the grit removal system and not have to deal with all of that stuff downstream. So the technology specifically, how could you remove grit? So you can do it really simply. A detritus tank, you know, just hold the flow back for a bit, let it settle out. You know, that is an option. To be fair, you wouldn't see this at a medium or large size wastewater plant, but you know, maybe for a small plant it can make sense. So you would allow the heavier stuff to settle, the denser stuff to settle, maybe the lighter stuff, the fats, oil, and greases to float up to the top, take off the effluent somewhere in the middle of there. And over time, just let it build up. You know, come in with a vac truck every few months, every year, whatever it is. So that's an option. You know, simple, nothing to do really, very simple. Might make sense for a smaller plant. Going up in complexity, you could do that a little bit more engineered. So a little bit more sort of controlled on the flow, horizontal flow here. Going to some kind of a sump where you could extract the accumulated grit using a pump. So now you're not into vac trucks. Now you're into pumped removal, probably periodic pumped removal. You probably wouldn't run that continuously, but a little bit more engineered though. You can avoid so much of the organics settling out, for example. Getting into the sort of real grit removal, if I can put it that way, the sort of engineered systems, then an aerated grit chamber is where you start getting into things that make sense for medium and large size plants. So to walk you through this, if you look at the top right of that graphic there, that's where the influent comes in. You can see the arrow sort of going through a weir, I guess an inlet, into the tank. Then the flow passes down along the tank towards the front of the screen as you're looking at it. But also air is being introduced on one side. So you can see that on the side you've got an air diffuser there, only on the one side, normally sort of medium coarse bubbles. What that does is it gives you an air lift effect. So as the flow is coming along the tank, you've also got air lifting it from one side, and that causes a spiraling pattern, helical flow pattern. The reason you do that is by spinning the flow. When it's on the downward spin, so to speak, when those grit particles are sort of heading downwards, they're more likely to settle out into the base of that tank. So then you normally have a scraper or some kind of system to extract the grit from the bottom of the tank. You also get some turbulence going on there, some shear forces, and that can help to separate organics from grit. Like I said earlier, that's a key reason for doing grit removal, or a key part of grit removal, separating organics from grit. So aerated grit chambers is certainly quite a common technology around. It was installed really, it was the standard for many years. But these days things have moved on a little bit, and really these days new systems, new wastewater plant upgrades are going to involve some kind of vortex grit removal process. What we're looking at here is a pretty common design. Some people would call this a 270-degree grit chamber, and that's because where the influent comes in, so looking at the plan view, the smaller channel on the far left there is the influent channel. Comes in right on the tangent, right on the edge of the chamber, on the round chamber. Then the flow goes around about 270 degrees before then exiting out of the other channel, the effluent channel, outlet channel, right at the top of the screen there. So that's about 270 degrees of rotation. That's why they're called 270-degree grit chambers. As well as the flow coming in on the tangent, which helps to give you that spinning, that vortex, you often see paddles in those kind of systems to help induce the vortex, to spin the flow as it goes around there. So that's what you're seeing on the section view there. The two paddles driven by a motor and a gearbox. The other thing you're seeing sitting on top of that grit chamber is a grit pump. The grit pump is connected to an extraction tube that runs right down to the bottom of the grit chamber where the grit accumulates. So how these things work is you have a weir on the outlet channel, and the idea is that by the time the grit has done that 270-degree rotation, it has settled just enough to not go over the weir. So the water goes over the weir, the grit keeps settling. So over time it kind of works its way down into the bottom of the chamber and accumulates in the grit well, and then is pumped out of there periodically. Pretty common design, lots of manufacturers on the market offer these. Where the grit goes from the grit well, so after it's been extracted by that pump, is normally to a grit classifier. The grit classifier is kind of two components really. Hydrocyclone, you can see that sitting on the top there on the cross-section view. And you see on the diagram on the right, that's sort of what's going on in the hydrocyclone. It's a vortex system again, a kind of intense vortex system. The idea there is that only the really dense stuff gets out of the bottom of that vortex, about 10% in terms of flow, and that drops down into the main part of the classifier, into the basin itself. And most of the water, about 90% of the water, goes out over the top. So it's a way of concentrating down that sample, get rid of most of the water. Not sample, but the grit, concentrate the grit, get rid of the water. Also shear forces, again, to give you some organic separation. So then the grit drops down into the main basin. In the main basin, you've got a screw. So water also overflows from that basin, and the screw intermittently turns, lifts the grit up along the channel in the bottom there, and dumps it out into a grit bin. You can also have grit washing in there to sort of sprays to clean up the grit before it goes into the bin. So those are the kind of generic technologies. Now just a little bit on what we offer, Veolia. Some folks know the name John Mounier. It's a long story. John Mounier was a guy who founded a company in Montreal in 1948. That company made headworks equipment, pre-treatment screens and grit removal equipment, and Veolia acquired that company. Veolia is this big global corporation, so we've kept the name John Mounier for our headworks equipment. So if you're confused between all of this, John Mounier is now a brand offered by Veolia. So first Mectan system, and we call all of our grit removal systems Mectan one way or another. Mectan's in the name. So we put the first one in 1981. That was that 270-degree design. We call that one the Mectan Classic. And since then we've put in a bunch. You can see the numbers on the screen here, mostly in North America. We make these in Canada, in Montreal. We fabricate this equipment in our fabrication facility in Montreal. This is an overview of the Mectan range. So going across the top, you've got the model numbers and the diameters. So these are standard sizes, pre-engineered standard size systems, going from 1.2 meter diameter chamber all the way up to 7.3 meter diameter on the far right-hand side there. So that's the range of sizes we offer. Up to 3.5 meters, we're able to offer those in self-standing steel tanks, stainless steel tanks. When you get above 3.5 meters, then shipping's not an option, so you need to go into concrete at that point. So anything above 3.5 meters is going to be offered in concrete. So you see in the middle there, you've got the Mectan C, that's the classic, the 270-degree design, and the Mectan V. The V stands for vari-angle. I'll talk a little bit about that in just a moment. Both of those designs, the classic and the vari-angle design, will give you the same capacity for a given diameter. So up at the far right, that 7.3 meter diameter chamber will give you nearly 300 megaliters a day of capacity, 295 megaliters a day of capacity, a lot of flow. The new system we just recently introduced, and I'll talk a bit about that as well, the BioMectan, is currently only offered in stainless steel tanks. We don't currently offer that in concrete, so that goes up to the 3.5 meter diameter. But it gives you more capacity for a given diameter. So you can see the numbers here. A 3.5 meter diameter C or V give you 40.5 megaliters a day. The new BioMectan gives you over 50.7 megaliters a day. Okay, so a little bit about the V. The vari-angle, really what we were setting out to do here primarily was capture more of that fine grit. When you think back to that classic design, the grit particle having to settle before it gets to that outlet weir, the denser grit, no problem. The bigger grit would not get over the weir. It would have settled enough to avoid overflowing. But the fine grit, you know, some of that would get out over that weir. So it was about trying to stop that kind of short-circuiting, I guess you could call it. So how we did that was to put a separator disc in the middle of the chamber, about halfway up the chamber. And then we bring the flow in underneath that disc. So you can see the inlet channel becomes a tunnel, it drops down, becomes fully flooded, and the influent comes in underneath that disc. Vortex is in there, it spins around, and then the flow has to get up through the middle of that disc. And that's how we stop the short circuiting. It's pretty hard for even the fine particles to work against that centrifugal spinning force. They've got to get against that force to get up through the middle. So it does a better job of capturing fine grit as a result. The other thing that does is it gives you separation. So the inlet is really hydraulically separated from the outlet. And that gives you the ability to put the inlet and the outlet channels wherever you want. You can configure those, you know, wherever you want, 360 degrees of flexibility in how you put them around that chamber. You can put the inlet directly above the outlet if you want to. That's why we call it the vari-angle. So that gives designers a lot of flexibility in how they lay their plants out. It gives people the ability to do retrofits more easily, and that's what you see on the bottom right there, that graphic. That's an aerated grit chamber that was upgraded with Mectan Vs, and you'd need the V, the flexibility of the V to be able to do that kind of a design, and that gives you more capacity. It gives you better grit capture in the existing infrastructure, in the existing basin. This is an example of another project we did with the Mectan V. It's in Ontario, Sudbury, a big plant. So we put in 2 of the 6 meter diameter chambers. You can see those on the graphic there. 2 of the grit classifiers. You can see them on the right of the graphic. And again, you wouldn't be able to do this without that flexibility in design. So it helps designers to do compact layouts, you know, more efficient layouts. And you can see on the pictures on the right, in fact, the bottom photograph there, you can just about see a guy doing the install. He's putting in the separator disc. So that's a 6 meter diameter basin, the chamber, just to give you a sense of scale there. So about a year and a half ago, we introduced to the market a new product, the BioMectan. The purpose of developing this product was to go even better than the V in terms of grit removal performance. And again, really thinking about that fine grit, trying to get as much of the fine grit out as possible. But also to focus on organic separation. So with the V and the classic, the C, you get some organic separation as a result of those paddles in the chamber. You also get organic separation in the grit classifier, in the hydrocyclone there. But with this design, we were thinking, well, how can we do the best possible job of organic separation in the chamber? Because we realized that if you can get the organics off the grit, you can capture more of the grit, because then you get the density back, right? You get rid of the fat, and then the thing will settle, that eggshell. So that was really what we were thinking about here, better grit removal performance and organic separation. So how does it work? The first bit is just like the V. That separator disc was a good design, so we figured let's keep that, let's work with that. So the influent comes in underneath that disc, just like we saw with the V, does a vortex in the bottom there, and then the flow has to get out through the center of that disc. What's different here is you can see now those blue arrows, the upper arrows, are kind of peeling off to the side. That's because they've got to get around that cone. You can kind of see the cutaway there of a cone. So that peels the flow off to the side, and that gives you a dead zone in that middle area where the particles that are coming up kind of get caught up because their direction is kind of into the middle, and then the flow peels off to the side. So then the flow goes up around that cone, out over an annular weir, and then out of the effluent. That annular weir gives you complete hydraulic separation, even more so than the V. So with that, you can do whatever you like on the outlet. It's completely flexible. You can go crazy, put right angles, whatever. Complete hydraulic separation. So what's the grit doing? Hopefully you can see this on your screens, the red grit particles there. So again, the V, the bottom bit, just like the V, collecting the grit that gets thrown out to the sides from that centrifugal vortex force. The lip on the separator disc, again, avoiding that short circuiting, getting the grit to accumulate in the bottom of the grit well, and then you do the extraction from there. But then you've got that dead zone where the grit is going to get hung up. So that's why we put that cone in there, to create that dead zone deliberately, because that's where we do this organic separation thing. How we do that is by putting eductors in that area, in that dead zone. Eductors are kind of like jets. How they work, you can see on the graphic on the right there. We pump water into the eductor, and it's a velocity pressure thing. The higher the velocity, the lower the pressure. So what that does, that jet of water coming in from the left, as you can see, of the nozzle, draws in water from the surrounding area where those grit particles have got caught up. It's about a 1-to-4 ratio. So that pulls in those little fine grit particles with the organics on them, shears off the organics because you get very high turbulence through there, and that means that the grit particle now gets rid of that buoyancy aid, is able to sink, it's dense, and the organics get separated off and go onto the plant. So that was really the innovation that we introduced with this BioMectan, is these eductors and getting that organics sheared off, and that's what gives you the better capture. If it's got out from that bottom section of the V, that separator disc thing, then either it is extremely fine or more likely it's got organics on it. So that was what this was all about. Looking at this at the sort of system level, so what goes around this, we don't need the paddles anymore. So what we've put in the place is a centrifugal pump. You can see that in the bottom right there of the main diagram. If you've got plenty of plant water, final effluent water or whatever, you could use that as well. Bottom line is you need water for those eductors. You need constant feed of water to those eductors, and you need water to do the fluidization when you do the grit extraction, like I say, about once every hour. Then you need water to fluidize the grit that's accumulated in the grit well. So those are the uses of the water. You could do that with a centrifugal pump and take water just from the outlet of the grit chamber, degritted effluent, run it through a Y strainer and then put it in that centrifugal pump, or if you've got plant water, you could do that too. Then you see the grit pump here doing the extraction, going over to the grit classifier that we've spoken about. Some other systems on the market have got another step in there. After the grit pump, before the grit classifier, some systems have got a kind of cup vortex type of a system that washes the organics. So that is something that some systems need. This technology doesn't need that extra step, so maybe it's a little simpler. And something else we do to make it simpler again is to mount the grit screw, so the grit classifier can be mounted directly to the bottom of the grit chamber. And that's what you see on the photograph on the right there. That avoids the need for the grit pump, so makes the system even simpler. So what about performance of this new thing, this new eductor-based BioMectan thing? Well, it was a long development process. Spent a bunch of time and money on doing this. Early in it, we were looking at computational fluid dynamics. You can see that in the graphic on the right there, showing the velocities. What the CFD analysis showed is that we should be getting a better level of grit removal performance than the Mectan V, especially on the finer grit. So that's what you see on the graph there. That's what the CFD indicated we could expect. But CFD is all well and good. What about the real world, right? So we built one of these things, installed it last year in a wastewater plant in Quebec, Saint-Agathe. This is a bit messy, this picture, and I wouldn't recommend you do a permanent installation like this. To be clear, this was only there for a few months, demonstration project, right? So the pump on the left is extracting water downstream of the screens. So we're taking screened effluent, pumping that into the grit system. You can see that coming up. Not sure how clear it is. I'm not sure I can really point to things in this setup, but there's a manifold on the left that black pipe is coming into the grit chamber. That's the influent manifold. You can see a bunch of little tubes going into there. Those are the sample tubes. And the bottom left photograph there is what those tubes are connected to. So those bendy pipes are picking up sample from various locations in that influent pipe. The whole idea being to get that representative sample. Don't take it from one point, take it from multiple points. Same kind of thing happening on the effluent manifold that you see kind of pointing towards us in the photograph. And then the other pump on the right-hand side, that's the grit extraction pump. So that's the thing doing the intermittent removal of the grit, pumping it over to the grit classifier that you can see on the top right of the photograph. We were treating about 4 million litres a day of sewage through this, of screen sewage through the demonstration. So, reasonably representative piece of work. We were there quite a long time, setting this up and running a bunch of tests, different times of the day, different days, different weather conditions, trying to get really good data on how well this thing worked. So, a lot of work. I won't go into too much details about it all, but some of that work was done on site, some of the analysis kind of there and then. Also, some of the work was done in our lab. So you can see in the bottom right photograph there, that's our lab in our headquarters in Montreal. We were also doing some external lab work, having accredited labs do some of this stuff. So a bunch of different analysis, a bunch of test runs, a lot of data. I am not able to show you all the data, but just to try and give you a sense of some of it. So the top right graphic there, that's a particle size distribution. That was done through dry sieving by an external lab. It's a log scale. I won't go into all the details on that. The one on the bottom right, that was some sand equivalent size analysis, so that's the wet sieving method. So we were doing those two different types of method. The graphic or the graph on the left there, titled influent, you can see two different lines, a blue line and a red line. So just to explain what's going on there, the blue line is dry sieving. So just to run that again, you've got your sample, you dry it until you've driven off all the water, and then you sieve it through that stack of sieves. And then you look at how much sand you collected, how much grit you collected on each of those sieves, and that tells you your particle size distribution, how much sand you had, how much grit you had of different sizes in your sample. That's the blue line. The red line is when you've done the wet sieving and you've got that raw sample and you've put it into the Imhoff settling cone and you measure the settling rate and then you equate that to sand, the sand equivalent size. So that graph shows a clear difference. And this was the same sample, by the way. We split the sample in two and we did some with the dry and some with the wet method. And that showed that for that same sample, the sand equivalent size analysis indicated that there was a lot more finer grit. That the whole, as you can see from the graph, the line is over to the left-hand side showing finer grit. So those two different types of analysis gives you a different result with the sand equivalent size indicating finer grit. That's partly because that raw sample has still got organics on it. It's not to say that it's an inaccurate result, it's just a different way of measuring it. And in some ways you could say that the sand equivalent size could be considered even more representative because that's the raw sample, that's what the grid is going to do in your plant. So both have got a value to them, but it does show the difference in the results you get. The other really good thing that came from all of this work, and our boss was pleased with this because of the time and money we'd spent on it, was that we showed the performance was actually better than the Mectan V. That CFD analysis did actually hold water. So that led us to these performance statements. The Mectan V does a pretty good job. 95% removal of all grit particles down to 100 microns. That's most of the grit you're going to see coming in, and that's a pretty good level of removal. The BioMectan goes even further, even better, 75 microns, so 95% removal down to 75 microns. That is as good or better than anything else in the industry. There is no current product on the market that offers a greater level of removal than the BioMectan, so it's the best performance you can get. Something else important to say, these performance statements that you just saw are stated at peak flow, at the unit's rated capacity. So thinking back to that earlier slide, we had the 7.3 meter diameter chamber. That treats 295 million litres a day. that performance is stated at 295 million litres a day for that unit. But in the real world, these systems aren't typically running at 295 megalitres a day because they are maybe a little bit over-designed. We're thinking about a 20-year design horizon, and also because most of the time the plant isn't seeing peak flow, it's seeing something less than peak flow, right? Maybe it never sees that 295 megalitres a day. So in reality, that grit removal system is almost always treating a significantly lower flow rate. And with all of our Mectan systems, performance improves as flow rate reduces. So what you're actually going to see is better than those performance statements in real life. So a little bit on O&M. These things don't have a lot of O&M to them. There's a motor and a gearbox for the paddle systems, the Classic and the V. Set and forget, they run constantly, 20-year design life. You grease them, that's what you do, grease them once a week. People forget they're even there, but don't, because you do need to grease them. Then you've got the grit pump, that's a little bit more involved. It's a pump, so you've got bearings and seals. Again, there's greasing involved. These things hold up pretty well. They're normally, again, a sort of set and forget. You set up the timer, maybe you extract once an hour for 10 minutes per extraction, but that is user configurable. If you find that you're getting more grit at certain times of the year, some plants, the freshet, for example, if you're in a cold area, snow melt, you can see higher levels of grit, so maybe you increase that frequency every half hour or whatever. So it is controllable, but oftentimes people just leave it running at a set how it was commissioned. The grit classifier, there's the hydrocyclone, again, set and forget, but there is a liner in there that wears, so that will need replacing every few years. And then you've got the screw, motor, gearbox, bearing, packing gland. Nothing that an operator is going to be particularly unfamiliar with. This is not highly complicated stuff to operate and maintain. So with that, wrapping up now, I think we might have a little bit of time for questions, hopefully. So yeah, thank you for your interest. Hopefully that's been useful. Hopefully there were at least 2 things in there that were of some use for you. And if there were questions, then now's the time.
Chris, Jenny's just collecting some questions, if any, are coming in. But I would like to thank you very much.
Thank you.
EOCP thanks you.
Oh, thank you very much.
Gift for you. It's interesting. I spent most of my career, all my career in wastewater treatment, and the grit removal has, it is important. Even, I think there's going to be more regulation, particularly for landfill and the organic content. So this is something that's coming.
Interesting. Yeah.
Especially if you go to an incinerator, they don't want it.
Right.
So you've got other things that are changing in the world, and that's part of our business. Wastewater. There's always things changing, and it's good to see that companies like Veolia are expanding that R&D to meet those future regulations.
Absolutely, yeah. Things only get.
It never goes backwards. No, it never gets slacker.
It always gets raised.
It always gets raised.
But that's okay, right? I guess that keeps it fun. So,
that's right.
Yeah,
that's
absolutely.
right.
A couple of questions.
Yep.
The first is there a recommended material for grit pump suction?
Ooh, wow.
Oh, sorry.
So I can repeat the question.
You can
The question was, is there a recommended material for the pipe material for the inlet suction side of the grit pump? The short answer is no, I don't believe so. What I've normally seen is PVC is quite a common material for those pipes. You have the extraction tube as well. That's going actually down into the grit chamber. For those, we would use stainless steel. So those are the 2 materials I've seen on the suction side of the grit pump.
We've also seen glass line pipe. Anything that's hard, it helps reduce the wear. You don't eliminate it. You just slow it down.
Okay, the second question would be, can grit get classified into an organic or separated into an organic and non-organic grit?
So I guess non-organic.
Repeat the question.
Sorry, yes. So the question was, can grit be classified into organic and non-organic grit, inorganic grit? I'm not sure I entirely understand the question. The classified would be the word in there that maybe that separated, right? Okay. I think the short answer is probably not. The idea with grit is that you're trying to get a clean grit product, either because of the landfill, the sanitary side of things, as you were saying there, Jim, or because some folks even reuse grit. In Edmonton, for example, they do some grit reuse. So it's about trying to get the sort of purest grit you can, which would be organic. Inorganic. It's the inerts, and then trying to keep the organics in the plant. That's where you want the organics.
And that's what the version was doing in the last one with the jets, blowing the
Absolutely.
organics off the grit before it went into the separating section.
Absolutely. Yeah.
So it is coming.
Mm-hmm, mm-hmm.
So,
Maybe there's one last question, and then we'll be out of time. Are current systems, are current vortex setups adaptable, or do you need to totally replace them?
They normally have fairly specific design geometries. Sorry, I should repeat the question. Are vortex systems, let's say, reconfigurable? Can you upgrade them by tweaking them? I guess by reconfiguring them after they've been installed. Short answer is probably not really. No. For example, that Mectan V with the separator disc, they're halfway up. It looks like something you could just sort of bolt into an existing 270-degree design. So take a Mectan Classic, the 270-degree design, put in a separator disc halfway up and done, right? But it's not, in reality, it's not so simple as that, because you need that inlet tunnel, not just the inlet channel. So you have to do some civil works around that. And realistically, by the time you're doing those civil works, it's basically a full upgrade. It's practically rebuilding it anyway. So if you're doing that, maybe you want to do the perfect job, get the geometry just right for the Mectan V, which you probably wouldn't do if you just tried to bolt a disc in something that was already existing. And maybe you want more capacity anyway. If you're going to those kind of lengths, you might as well just sort of do a full upgrade, right? Great. Well, thank you very much. Thanks again.
okay. Well, thank you. We'll be taking a 15-minute break and back with our next presentation. See you in a bit.